Hi. All right, let's talk about Le Chatelier, or Le Chatelier, for those of you who care about pronunciation. But we're going to talk about Le Chatelier's principle. So we previously learned that stresses on a reaction at equilibrium cause the reaction to fall out of equilibrium. But equilibrium really is the place to be. It's where it's at. So the system's going to attempt to correct itself until equilibrium is established again. And this conversion, this getting back to equilibrium, is called a shift. And we can explain it, how it's going to happen, predict the direction of it, through Le Chatelier's principle. So Le Chatelier originally described his principle as follows. Here's the quote. Every change of one of the factors of an equilibrium occasions a rearrangement of the system in such a direction that the factor in question experiences a change in a sense opposite to the original change. Whew. Okay. If any of you fell asleep during that, I do not blame you. That is a mouthful. That is a lot. So here's an easier definition. When a system at equilibrium is subjected to a stress, so if there is a change in an equilibrium system, the system will shift to partially alleviate the stress and restore equilibrium. So it's if there's a change in the system is going to correct itself to restore that equilibrium because that's where it wants to be. So let's figure out how we can apply this to an actual reaction. So think about this reaction right here. 2SO2 plus O2 yields 2SO3, and then this reaction is at equilibrium. So think about what would happen to the forward rate, so producing your products, going from your reactants to your products, if we were to take out some of the oxygen from this equilibrium. What do you think would happen to the forward rate? Hopefully you shouted, the forward rate's gonna decrease, Miss Lambert. I love how I really feel like Dora the Explorer in some of these videos. So if you take away some of the oxygen, you have less oxygen available in the system, which means your forward rate is gonna decrease. It's going to stop happening so quickly. So we can explain why this is true in terms of collision theory. If you remove some of that oxygen, you have less oxygen particles available, which means that collisions are going to be less likely. And if you have less collisions that are going to be happening, there's not going to be as much product production in this system. So there are less O2 particles. Therefore, collisions will be less likely. So the system was originally at equilibrium. It doesn't like that a stress had been applied to it. If we remove some oxygen, that is a stressor on the system. It's a change that is happening in the system. So to counteract the stress, the system's going to shift to relieve that stress. But how? So if I take out some of the oxygen in the system, I am decreasing the amount of oxygen particles available. That means that my system has to go back the other way to increase the amount of oxygen that I took out. So more product will reverse into reactants. So we call this a shift left. It's all based on directionality. So to counteract the fact that the oxygen is being removed, the equilibrium is going to increase or is going to reverse. The reverse reaction will be favored to go back the other way to turn some of that product into reactant so that way I can get back to the oxygen that I was at before, the amount of oxygen I was at before. So I don't really love the term of shifting left versus right. It's not really something that is accurate in a system. If you think about the system that this reaction would be happening in, probably since we're in gases, it's in some closed container. Those particles aren't physically moving left or right when you're shifting your equilibrium system. So what I would prefer we say is that it's more appropriate to say it's a shift towards reactants. I'm moving in the direction of the reactants, so my products are turning back into reactants. I just think it's a little bit more representative of like what's actually happening in your system, so I think it's a better language to use. Plus, as we've already discussed, like 50% of women have left-right dyslexia, and I think that's just, you know, the war on women continuing, calling it shift left versus right. So I think it's better to call it shift towards reactants or shift towards products. So oppositely, if you had a shift right, it would be a shift towards products. So how do different stressors affect equilibrium? So there's a few things that can be classified as stressors on an equilibrium system, and we're going to talk about each of them. So first thing first, we're going to talk about temperature. So to make an accurate prediction, to think about directions of shifts in an equilibrium system based on changing temperature, it's best to think of heat as being a product or reactant and write it into your equilibrium equation. So if we take a look at the reaction up here, it's a phase change between liquid water and gaseous water. So think about, where does heat need to go in this system? Is this an exothermic process or an endothermic process? Do I need to release heat or do I need to absorb heat? So in order to go from a liquid to a gas, the liquid has to absorb heat energy. So that means that heat would be acting as a reactant. So I'm going to fill it in right up there. And then I'm going to say, where does heat belong? Reactant side. So liquid water will absorb heat energy and then turn into gaseous particles. So if we think about increasing the temperature, what are we doing to our system? We're increasing the amount of heat energy we add. So will this make the reaction shift left or right? Will it make it shift towards products or towards reactants? So this should make a shift towards products. Does that make sense? Well, yeah, hopefully it does. If you're at higher temperatures, what's happening to your particles? Your liquid particles are absorbing that energy. They're moving faster and faster. The faster they move, the more likely you've got collisions between those particles. Those particles are going to bump, exchanging all of that kinetic energy, and boop, turn into the gas phase when they get enough energy to break those intermolecular forces away from each other. So at higher temps, more particle collisions are likely, driving the forward reaction. So, one important thing that you need to know about effects of temperature. When you stress the system by changing the temperature, you also change the rate constant. K, lowercase k. Because the rate constant K depends on temperature. You also are actually affecting the equilibrium constant K as well, because that depends on temperature. So reaching equilibrium again does not mean that you are trying to achieve the same K value as before. All it means is you're trying to get the rate of the forward reaction to be equal to the rate of the reverse reaction again. All right, so now let's talk about concentration. Okay, so we can shift equilibrium by adding or removing chemical substances from the reaction vessel, which in turn shifts the reaction rate either forward or reverse until rate forward equals rate reverse again, and equilibrium is reestablished. So let's think about this reaction here. So this is dissolving. So this is taking solid NaOH, and we are dissolving it to produce Na plus and hydroxide OH minus ions in solution. So in solution, the NaOH is going back and forth between this NaOH and its ion forms. So what we want to think about is how the system would react if we added NaCl into the reaction solution. So NaCl is not represented in our reaction equation, but a piece of it is. So think about what happens when you add NaCl salt into water. It's going to dissolve. So if NaCl gets into solution, NaCl is going to dissolve to produce its ions, Na plus Cl minus. And now, boom, those two things match up. So by adding NaCl into the reaction solution, what am I actually doing? Well, I'm increasing the amount of Na plus ions I have in solution. So if I increase this, what's going to happen to the system? I've increased the amount of Na plus ions, so to reestablish equilibrium, the reaction has to shift back towards the reactants to relieve that stress. So I've increased the concentration of Na plus ions, therefore, reaction shifts towards reactants to relieve the stress. All right, now let's think about what would happen if I titrated or I removed some hydroxide from the reaction vessel. All right, so in this system, let me get rid of this, bye. I'm gonna take out OH from the reaction vessel. So I'm decreasing this thing right here. So if I decrease the concentration of hydroxide, how's the reaction going to behave? Well, I need to shift this direction. I need to shift towards the products. I have to alleviate that stress by making more OH to balance out with the OH that I took out. So therefore, because I'm decreasing hydroxide concentration, reaction shifts towards products to relieve stress. All right, here we go. Predict how the system would react if you added magnesium phosphate to the solution. What? None of those things are in our equilibrium equation right now. But think about what would happen if you added magnesium phosphate to water. This is a salt. So if this thing's a salt, it's going to dissolve. All right, okay, yeah, sure. Mg3PO4. I'm going to take this thing and it's going to dissolve, so it's going to break up into its ions in water. All right, yeah, I got that. Mg2 plus, PO4 3 minus. Okay, sounds good. Wait a second. Mg3PO4. This should be Mg3PO4 too. Oh, caught my own mistake. Yay! Okay, give me a second. Fix this. Bye. Okay, now we're correct. Okay, so Mg3PO4 2 dissolves into water. So what's going to happen here? Okay, I've got a bunch of ions floating around in solution. I've got 2 cations and 2 anions. Oh, weird. I have 2 dissolved ionic compounds all in solution. Double replacement reaction. Got to know your solubility rules. All right, so if I take that Na+, that thing's going to see if it's going to react with phosphate. Rule number 1, solubility. Anything in group 1, any group 1 metal, always soluble no matter what. So that means that that thing's not going to precipitate out. Cool, sitting pretty there. But now I got magnesium and I got hydroxide. Oh man, that's a bad combo. What's going to happen is our Mg2 plus ions in solution are going to link up with those OH ions in solution. And what's going to happen? They're going to precipitate out. I'm going to get MgOH2 solid. Okay, so I've precipitated this out of the solution. So effectively, what am I doing? I'm decreasing the concentration of hydroxide again. So if I'm decreasing the concentration of hydroxide by precipitating it out in solution, what's going to have to happen to my NaOH reaction? It's going to shift towards the products. Exact same thing as we said for this one. So effectively, because I am removing some OH from solution, I'm decreasing the concentration of hydroxide. My reaction is again going to shift towards the products to relieve that stress. Gotta know your solubility rules. All right, next one, pressure. Okay, so changing the total pressure of a system can disturb the equilibria of reactions that have gaseous species in them. So pressure, we really only care about when we're talking about gases. So if the pressure is increased in the system, you're going to have more collisions between your particles. So how does equilibrium reestablish itself? The system is going to shift to the side of the reaction that has less moles of gas. If it can decrease the amount of gaseous particles in solution, or in the system, it can reestablish that equilibrium. Alternatively, if you have a pressure decrease, you're going to have less collisions. The system has to correct itself by shifting to the side of the reaction that has more moles of gas. So I can increase those particle collisions again to get back to where I was before. So predict how the system would react if we increase the size of the reaction chamber from 1 to 2 liters. Size of the reaction chamber, that's not about pressure. Well, it's a good thing we're excellent at our gas laws and we remember that there is a relationship between pressure and volume, which this is talking about. What is that relationship? PV equals nRT. Hi, ideal gas law, love you. Okay, relationship between P and V, inverse. So what am I doing to my volume? I'm increasing it. So V increases, therefore P decreases. So I'm decreasing the pressure in my system. So what's going to happen? I got to go to the side that has more moles of gas. I have to correct myself. So if I take a look at the reactant side, I've got 4 moles versus the product side, I've got 2 moles. So which side am I going to go to? Decrease in pressure, more moles of gas. I shift towards the reactants in this case. So decrease in pressure, shift towards reactants. All right. Next up, predict how the system would react if you N2 into the reaction vessel. Oh my gosh, I'm so silly writing these notes. Predict how the system would react if you, let's say, add N2 into the reaction vessel. That makes sense. So if we add N2 into the reaction vessel, what are we effectively doing? We're going to be increasing the concentration of N2 in our system. So if I'm increasing the amount of N2, it's going to shift towards the products. This is going to counteract the shift. So increase concentration of N2, therefore reaction shifts to products to relieve the stress. All right, last one. Predict how the system would react if you added the inert gas xenon to the reaction mixture. Okay, so here's where it gets tricky. An inert gas, the word inert, means non-reactive. So if you think about where xenon is on the periodic table, it's in group 8. Things that are in group 8 have how many valence electrons? 8. So why are these things inert? They're already highly stable. These things don't want to react. They don't want to lose or gain or share electrons because they already have filled valence shells. So xenon is an inert gas that doesn't want to react. If you are adding gas to the system, essentially you're going to be increasing the overall pressure because you're putting more particles. However, this will not have an effect on the equilibrium position of the reaction. Inert gases do not affect equilibrium positions. Key, need to know. So let's write it out. Adding an inert gas while increasing overall P, actually comma, while increasing overall P, will not have an effect on the equilibrium position. My cues are really getting kind of crazy lately. Okay, not have an effect on the equilibrium position. All right, last stressor, catalyst. Okay, so adding or removing a catalyst to a reaction has no effect on the equilibrium condition. Wait a second. No effect. I know words. Okay, adding or removing a catalyst to a reaction has no effect on the equilibrium condition. But what it will mean is that your activation energy barrier is lowered, which makes your particle collisions more likely to get over that activation barrier. So it does mean your system will be able to reach equilibrium faster. And it can happen at lower temperatures because your particles don't have to have that much energy. So it does make reactions more profitable, but it has no effect on equilibrium position. All right, so what you're going to do is take a look at this last question here with the and get some practice in. So what this is saying is that the left-hand side, the reactant side of this reaction, NO2, has a brown color to it when there are more reactants than products. If your reactants are favored, you'll see brown. Alternatively, if you're on the other side, N2O4, you will see a colorless situation. Or I guess you won't see anything because it'll be colorless if your reactants are being favored here. It also tells you that this reaction is releasing 58.9 kilojoules per mole of energy, so this is an exothermic reaction. So what you're going to try and do is think about what's going to happen to the concentration specifically of NO2 and the color for each of the following stresses in this reaction. Once you're finished, check in with the answer key on Canvas, and then you're donezo.